Yeah, like I said, I requested them to bring one, but unfortunately, since we didn't have it submitted through the form, yeah, yeah. So I thought I emailed you the link to the equipment borrowing one. Okay. Yeah, if you could just try. I mean, honestly, if you just try to stay here or pick it up with the ceiling mics, like the ceiling mics will work, but like, I mean, it's just not going to be as clear. But they definitely will come through though. Let me. What? Oh, someone talked through. Okay. Yeah, we can give it another minute and see if they show up. But I mean, I sent them a message. But, I don't know if they can really go. Let me call them.
First class of the semester, I get to use Christine. Lovely. Thank you.
They might bring it halfway through class.
No worries.
But
That should be fine.
yeah, so like I said, I can try to increase the volume a little bit with the ceiling mics if you want to stand by the gooseneck mic there. I know you like to move around. I'm sorry.
That's okay. Yeah. So the first half of the class is mostly logistics.
Yeah.
Covered.
Okay.
So
Yeah, like I said, I messaged them. Like I hope they can bring it, but I can't promise like that they can. That's a different department.
Good morning. Good morning. And welcome to this new edition of Intro to Deep Learning. So before we begin, this is a dumb classroom, meaning no smart devices besides yourself allowed. Shut your laptops, turn off your phones, put them, pocket them. You will be required to use your laptops and phones occasionally when we have polls. So you see that at 26 up there. Before you shut your laptops, yeah, just bear with me. There will be a Piazza poll at the beginning of every class. You go up to the poll number shown on the slide, regardless of where you are, whether you're on Zoom or whether you're in the classroom. And sign up. So this is how I keep track of your attendance. So this is I need this. Get an idea of who's in the classroom, but I can also have class.
Good morning, please.
Making sure that you're engaged. And so we will tag either the other folks, 4 of them in each class, where when you ask a question, they're supposed to respond. So these are only 5 instances where you're allowed to use your phone or your laptop. At other times, please keep your laptop shut. And if you must use your laptop, I won't stop you. Don't do it in this classroom. It's so important. Go outside, finish your business, and then come back in. Right? And if you insist on opening your laptop in this classroom, I will keep I'll stay quiet here. Wait until you're done with your business, because I do not intend to speak when somebody has their laptop. Right? Okay. The class will begin with your laptops. Those of you at the back, so and so will speak. Some rules apply to the front rows as they do to the back rows. Gets my laptops. All right, I usually have a lapel mic. Today we will be getting the lapel mic halfway through the class, hopefully. So I'm going to try to speak from here. If those of you on Zoom cannot hear me, just let me know. So are we on Zoom? Somebody grabs it. I'll call my TA. So let me begin. Hopefully, by now, you've already seen the logistics post of Piazza. There was a post of Piazza welcoming everybody to the class. It gives you some idea of how the class is being run. And we also have a logistics lecture recording that's up on the web. Hopefully, you've all seen it by now. So if so, you are familiar with the logistics of the course. I'm not going to spend much time on it in this lecture itself. I will go over a few brief points. If you haven't seen that, please watch this lecture at once, because we will not be answering any questions related to logistics on Piazza if the questions are answered in the lecture. So you're expected to have watched it. You've been to the course website, deeplearning.cs.cmu.edu. This is the course website that you use every semester. And if you haven't done so, please visit it at once. The course objectives, logistics, quiz and homework policies, grading policies, all of these have been explained on the website. Some of these are subject to change. As always, we will be dynamic, we'll be and depending on how the semester progresses, how the feedback you get from your students, some things will change. And familiarize yourself with all of this information, because this is going to affect the rest of the course. Now, you should already have signed on to Piazza, and you should have verified that you have access to. Yeah, take a step.
People are saying that the voice is not coming.
Okay, I'll speak on.
Also, your screen is not, it's showing your screen.
What's that on screen?
It's just showing as a red block.
Okay.
Yeah.
Apparently share on screen.
Yeah, you just gotta stand by the neck, sorry.
No, the screen is not, it's showing the wrong screen. So, did that get set right? So we can just go up and show it. Well, let me continue, because these things, even if you are on Zoom, hopefully things get set right. And being unable to see the screen right now is probably not such a critical problem. But by now, hopefully all of you have signed up for Piazza and verified that you have access to the campus and of the lab. Guys, there is room. If there isn't room, there's a chair out here. You'll get a note on forming study groups. So the way this course is run, we encourage collaboration. We're not very picky about with others. In fact, believe that you learn best from your peers, not from me. So which means that we will encourage all of you to work in teams and to assist you in this to form study groups. Now, before you begin, here's a bundle of papers. Please pass this around. Everybody keep one sheet, like so. This is it. Go ahead. Let's take one sheet and pass it around. This sheet of paper is the most important thing you'll have in class. And here's what you're going to do with it. You're going to start off by folding it in half, like so. And then fold each half again in half inwards. If you're wondering why I'm doing this, you will find out shortly enough. And I hope you have pens. If not, borrow your neighbor's pen. And this thing makes a fantastic video. Come on down. So this thing forms a fantastic name tag. We're going to just have this little pyramid in front of you in every class. And you're going to write your name on it. This is how I will know who you are. And I am going to be calling out names. When my lapel mic is here, I tend to wander all the way down to the bottom of the class and calling out random names. So just so you know, I make sure not only that you're engaged, but also that I'm not picking the same person again and again because I just know one name. One guy, just bear with me. Sit somewhere. I apologize. Okay. So if you have not filled up the forms for the study groups, so please do so immediately, right? And then here's our course philosophy. We want every one of you to get an A, but we want you to earn it. So this means that we don't have a crazy grading scheme with curves which ensures that 50% of the class gets B's. That's not how we do it. We are grading you on absolute performance, but also compared to how the rest of your classes performed. So I'm not giving you a free A. It's going to be incredibly hard to get in this class, but at the end of the day, I promise you 70% because we will make you work. And we are going to provide a ton of resources. We have 25 TAs. They hold dozens of office hours. 40 office hours each week, in fact. We're going to we form study groups. You all have free access to my office. You can always come in anytime if you have doubts. I look intimidating up here, but I'm not. We answer pretty much everything on Piazza. Our response time over the past several semesters has been on the average about 5 minutes, which means that, and we get up to 40,000 questions a year, or 20,000 a semester. And we manage to respond to all of these with a wait time of 5 minutes to make sure that you guys get the best you can. We will have hackathons. We will have other ways of making sure that you get to interact and you get to learn. But at the end of every one of you is going to have a TA mentor tracking your performance. At the end of the day, we're going to do everything we can to make sure that you actually do well in the course, that you have learned the subject. And as somebody once mentioned, that you're a ninja on the subject. So that's our job. And if you give it your best, you'll get an A, right? And again, it's a lot of work, and this is not the only course you will be taking, which means that you will be under stress. Every one of your instructors and every one of the courses you take is going to pretend that that's the only course you're taking. So if you're under stress, or if you feel overwhelmed, or if you have problems, talk to your TA mentor, talk to me. We will do our best to help you. And I'm not. Yeah.
A lot of people can't hear you. If you could stand by them.
Okay, so thank you. Every semester we have a certain number of students who have stress-related issues, and they end up needing help. I encourage you very strongly to reach out because we are here to help you. And we will do everything we can to make sure that you get through the course comfortably. It doesn't mean that you're going to get through the course easily. You will have to put in the work. But we will do our best to help you in every possible way we can. So we have hackathons every week. And on 31st, this Saturday, we have a meet and greet plus lab hackathon, which means we'll post a room, and we expect any of you who wants to be there to be there. We'll have pizza, so that's usually a good thing to bring in the students. Now, most of you are strangers to one another. That's your chance to go meet each other and help team up, form study groups, so just to get to know each other. So because in our experience, my experience over 25 years of teaching, you don't learn anything from me. A small number of you learn stuff from me. The rest of you learn from those people. So, having friends, having your, being able to discuss with your peers is a major thing. Again, we expect each of you to work individually. You don't submit your friend's homework. You don't submit your friend's code, but then you can refer to this person for help, right? And so this is your opportunity to form friends. This is also a place where we will conduct labs and help you with the actual assignments and quizzes and such like, so do be there. Now, here are the course objectives. We have 3 of them. We're going to understand some of the theory behind neural networks. By the end of the semester, hopefully you'll be able to build your own neural network components, which means that if you find yourself on a deserted island somewhere, and for some reason you have a computer, and for some even stranger reason you want to build a deep neural network, you will know how to do it. And you'll also know how to work on large-scale problems. So for this, on the business of understanding the theory, we'll teach you the what, the why, and the how, basically the math, and occasionally we'll delve into the history. And this, knowing the what's and the hows, will help you contextualize how you can actually build your own systems and work on large-scale problems. Now, this means that it's also going to assist you with research, applications to grad school, and maybe job interviews. This is a big thing. A lot of the stuff we cover in class here ends up in your job interviews, so do pay attention. Now, you have 4 homeworks. Each of them has 2 parts. In part 1, you will be writing your own code and building your own toolkit. And so that's where you learn to build your own network components. And then each homework has a second part where we give you gobs of data. And you're supposed to build state-of-art solutions for some problems. So this is where you learn to actually work on large-scale problems. Now, those of you in 785 will also have to work on a course project. The course project may relate to any of these 3 objectives. My lecture style is very verbose. I speak a lot. I have lots and lots of slides. In one lecture, I have 270 slides for 80 minutes. How do I get through 270 slides? That's because I animate stuff mechanically, because I find that's the only thing that works. Anytime I do something automated, if I change my laptop, it doesn't work. So given a choice between deriving an equation on the board and showing you 65 pictures, I will show you 65 pictures. If you don't like this, if this is not the style of lecturing you are familiar with or you're comfortable with, you should. This is not the course for you. Please shut your laptop. Yes, right. Thank you. All of you guys, shut your laptop. Those at the back, shut your laptop, right? As I mentioned, this is a no laptops course. You guys there, please shut your laptops. No laptops and no phones in this classroom, right? And we have in-class polls for class participation, where we post polls at random times, and these are posted on Piazza. You must respond. You're expected to attend class, but some of you can't. Some of you are in horrible time zones. Some of you will be sick. Some of you have other, unavoidable engagements, in which case you just let me know, and we'll make sure that you get the necessary exceptions. So it's an interactive class. I like questions. And there's a common problem among students. You feel embarrassed to ask questions because you think maybe you didn't get it right. Maybe you're making a fool of yourself. You are not. So here's the rule. If you don't understand something, the problem is not that you didn't understand. The problem is that I have not explained it sufficiently well for you to understand, which means that you should ask. Please do not be embarrassed. There's no such thing as a stupid question. There's no such thing as an embarrassing question. There's no such thing as a silly question. Everything is fair game, right? And I'm going to try all kinds of strange tactics to encourage interaction because I want to keep the students engaged. 80 minutes of lecture is horrible. I fall asleep delivering 80 minutes of lecture. I expect you to fall asleep listening to me, right? I'm going to try various tactics to keep you awake. And keep your smart devices shut, except for answering polls. Some of you may want to view the lecture slides on your tablets, particularly if you're sitting at the back or take notes. If we find you using your devices for any other purpose, and I have spies all over the classroom, they are you, then I will ask you to leave the classroom, finish your job, and come back in if you wish to. Right? Last but not the least, if you haven't already observed it, I'm handicapped. I'm using this thing here because I can't point. So this is all I can lift. I'm going to use this to point to things. I'll bring strange stuff of this kind, swords, pointers, and such like, because I found that the Halloween store is the best place for pointing equipment. So I can't clip on my lapel mic. And sometimes I ask my TAs to do it, and I've had students complain about this. They find this behavior inappropriate. If you think it's inappropriate, this is not the classroom for you, right? So, any questions? Yes.
So will the attendance polls be announced, and then we take out our laptops?
Yeah, yes, there you go. You'll have the polls. Finally, I'd like all of my TAs to stand up, please. And you guys can also write your names in big characters. Put it one down. So, come on up front. So these folks here, these are the heroes who are going to be supporting you through the semester, right? We have a great many of them. So, and this isn't the entire set. We also have TAs in Kigali, 3 of them, and don't trip, right? And so it's a very large number of these guys. Please familiarize yourself. I'll recite all of their names, so there are so many of them that it will take 10 minutes. But somebody take a snapshot. Can somebody take a picture? Yes. And we will post it on Piazza. And not to the classroom. Not be a part of it. We'll post this, and if any of the rest of you want to take pictures, please do so as well. We'll post this picture on Piazza. It will be pinned, and I will write down the names of every one of these people on the post, so you know who to go to. And if you encounter one of them in the corridor, you know you can corral them and ask questions. So, thank you, guys. Any other questions? Anything on Zoom? All right. Again, feel comfortable. Guys, while I greatly appreciate your writing this, in the next class I will actually bring marker pens, because trust me, I can't read this. Not because the handwriting is bad or anything, it is, but you know. I can't, it's too faint for me to read, right? So, I think that's any questions. People on Zoom, do you have any questions? Anything? Okay, so let me begin, right? That's it. That's the introduction to the course. We jump right in. So here's what. We're going to go to today, we're going to go briefly through a history of neural networks, connectionism, its relation to cognition and the brain, and its contrast to conventional computer architectures. We will look at early models and their limitations, and introduce modern neural networks and what they can compute. So the reason you're all here is because by now, everybody knows that neural networks are going to take over the world. Now, I've been teaching this course for 12 years now. And for the first 6 years, my typical classroom consisted of anything between 6 and 12 people. Nobody was interested because, it didn't seem like a hot subject, and it wasn't going to win you a job. But then, what has happened now is that we found that these things have been applied to pretty much every problem you can think of, and they have established the state of the art. And the best thing is, this seems like a simple solution to so many problems that those of us who are mathematically handicapped can still get along in machine learning life, thanks to neural networks, right? So this is great. But all of this changed, like I said, the first few years that I taught the course, nobody really turned up for my classroom, in my classroom. And then there was a switch, and this was around late 2016. So what happened? Here are some examples of the things that happened all at once. For 50 years at that point, we had been trying to automate speech recognition. IBM built its first speech recognition system in the 1950s. But in 2015, if you use Siri or one of these tools, to perform speech recognition, it was mostly a party trick because what you said and what came back were not even connected. They were not related. And then for the first time when was this? This was October 20th, 2016. There was this report that Microsoft had built a speech recognition system that outperformed human beings on a specific task. But that's pretty amazing if you think about it, right? And they did it because they had switched to using neural networks. These days, of course, automatic speech recognition systems are better than all of us on most tasks. So also machine translation. Again, what is the date here? This must be in, I don't know if I can find the date, November 2016. See the date again, right? So in October 2016, if you used Google Translate, which was the best translation system of the day, to translate from English to Spanish and translate the output back to English, what came in, what went out and what came in would not be the same. And we mostly use this to entertain ourselves in parties. It wasn't a practical thing. And then suddenly, in one day in November 2015, without much hoopla, Google Translate became so good that professionals were using this to generate the first cut of a translation. What happened? We began using neural networks. And same thing. The basic metric for what was an intelligent system was often considered intellectual games. Now, the earliest intellectual game was that we pit computers on was chess. But then by the mid-90s, we had already figured out how to build chess games that could beat humans. Now, chess is one of those games which is purely intellectual. You don't see animals and other beings playing things like chess. It seems to epitomize the notion of abstract intelligence, and computers beat it. Anybody know where the first chess game that beat a grandmaster was built? Anyone? It was right here in Carnegie Mellon. So we built the first. It started off as a side project for somebody. Eventually, it became his thesis. We built the first. It was called Deep Thought. It beat a grandmaster. The person who built it then went off to IBM and built Deep Blue, which beat Kasparov, right? Garry Kasparov, who was the world champion of the day. And no human chess player has beat the best chess games, automated chess games ever since. So yeah, we've beaten chess, but then Go was something like 60 orders of magnitude more complex than chess. And so computers never really managed to beat humans at chess, and we continue to think that this epitomized human intelligence, the game of Go. And we couldn't get any computer algorithm to come close to beating the human champs or even amateurs until 2016. And then we had AlphaGo, which beat the then world champion Lee Sedol. And these days you have computer programs which can start learning to play Go, and 3 hours later they can beat every human on the planet. And that's because we switched to using neural networks, right? Or something like this. Here, collection of pictures, and there are automatically generated captions over here. I don't know if you can see them, but they're pretty good, right? Man in black shirt is playing a guitar. Construction worker in orange safety vest is working on a road. Now, this appeared in 2016. This was the first time that we actually had automated algorithms that could just look at a picture and describe them. Now, as you can imagine, this is a pretty phenomenal thing. We didn't expect any of this kind of intelligence from a computer program in just the year prior. And here we are, thanks to neural networks. So, and so on. And now, of course, here's what ChatGPT can do. This was a picture that my ex-TA Karan took in his room. and just fed it to ChatGPT and said, describe it. And here's what it says. The ceiling appears to have several noticeable water stains. He didn't notice it, but ChatGPT did, right? And says, which could indicate potential water damage. The stains seem to be spread across multiple tiles. There are posters on the wall, there's furniture and clutter. And then only after ChatGPT told him that did he realize that there was a blue jacket somewhere in his room. He didn't know. Now, this is amazing, right? This is better than most human observers, and this is where we are right now, right? And even better. So, and many other problems, from astronomy to healthcare, even predicting stock markets. Everywhere, everything that you can think of, we have neural networks being employed, and they are phenomenally good. So, what are these neural networks? Right? We've sort of come to the conclusion that they are actually game changers. Starting from 2016, they've gone from place to place. At this point, neural network-based AI is everywhere, which is why you guys are here. But what are these things? Now, in every case, it's some kind of a black box, as far as you guys are concerned, where stuff goes in and stuff comes out. If I was performing speech recognition, a voice signal would go in, and a transcription comes out. If I were captioning images, an image goes in, a caption comes out. If I'm playing games, the current state of the game goes in, and your recommendation for the next move to make comes out. But what's in the box? We don't know, right? So to understand what's in the box, we have to realize something about the tasks that we just looked at. Each one of these tasks, recognizing speech, captioning images, playing games, these are basically human actions powered by the human brain. So there's something about the way our brain works which enables us to do all of this, which means perhaps if we want to understand how to do all of this, we have to look at the human brain. Or even before that, we want to look at how humans think, cognition. Now, here are all the things humans can do. We can learn. We can solve problems. We can recognize patterns. We can create. And here's the most amazing thing. We can come up with things with no stimulus at all. Most of the best ideas you come up with are thought up in the shower. You have no external stimulus, maybe except perhaps water falling on your head or something. And you can think up of benzene rings and you name it, right? Or art or things that you can write. We're able to cogitate, we're able to create, and we're able to do this without external stimulus or seemingly without external stimulus. So how does all of this happen? We would like to be able to emulate this human process of cognition. But to emulate this, we need to know how humans work and how do they work. The problem is, as Marvin Minsky says, if the brain was simple enough to be understood, we would be too simple to understand it. But that hasn't stopped us from trying, so we continue to try. And the earliest models of cognition go back 2,500 years. So the earliest recorded model was by Plato, I think. So anybody recognize this painting? I think it's the School of Athens. You can find it in the Sistine Chapel. It shows all of the scientists of the day going back into history, to the earliest prehistory, in a single painting. So I think in the middle you have Socrates and Aristotle and various others, Diogenes and so on. So going back to Plato's times, Plato was the first person who actually recorded a theory for how the human brain worked. And his theory, which was the ruling theory for the next 2,200 years. Now that's pretty amazing, right? Was based on associations, associationism. Now what is associationism? We're familiar with it. All of you must have heard about Pavlov's dog, where he would ring a bell and the dog would begin to drool. So this is because the dog had formed an association between the ringing of the bell and being given food. So association, that's how the theory was, that's how we operate, and this is actually a pretty good theory. It is in fact how we operate. Now think about it. Every time you observe lightning, you hear thunder after a while. So once you have formed this association, if you see a lightning, you expect thunder. If you don't observe the lightning, but if you hear the thunder, you will believe that a lightning must have struck nearby. So you have formed the association. But then, and we form various associations of this kind based on our daily experiences. And thereafter, when you perform any kind of inference, any kind of logic, it's based on the associations that you have formed in your head. But then the question really is, this hasn't, the fact that we are doing this through associations is all very fine. And in fact, what is math? Math is just a functional form of associations. You're associating an input with an output. So even the most modern machine learning algorithms of today are effectively association-based mechanisms. But where and how are these associations stored? For this, we got to go back and look at the brain. By the mid-1800s, thanks to improvements in microscopy, we knew that the brain was a massive network of basic elements, which we hadn't yet begun calling neurons. The term neuron came later, but we had already knew that the brain had lots of very specialized cells and that they were deeply interconnected. That's fine, but how does that actually store all of the information, these associations, the ability to come up with inferences? That idea, so again, if you look closely into the brain, this is what it looks like. You have many of these cells, billions of these cells, and these neurons. Each neuron has many incoming connections from several neurons. Each neuron connects out to many neurons. That's how the network is formed. So the brain is a network of neurons. And this guy, Alexander Bain, came up with the first model for how this performed computation. So this was in 1873, he wrote a book called Mind and Body, and he theorized that how the brain functions and what it stores is entirely a function of the connections between the neurons. Now, this was a pretty incredible insight, and not only did he have this insight, he even came up with some models of this kind. So here, for example, is one of his models. He showed how the same connection of neurons can produce different outputs for different inputs. So here, for example, there are 3 inputs. There are 3 outputs. And if A and B, now assuming that all the inputs are binary, 0 or 1, if A and B are 1, then X fires. If A and C are 1, Z fires. If B and C are 1, Y fires. So you just have one network, but depending on the pattern of inputs, you have different output patterns. Now, this was one of Alex Bain's models. He even came up with another model, extensions, where he showed how simply changing the level of the input could change the output pattern. Here, for example, X gets 2 copies of the input, Y gets 3 copies. So if the input is faint, only Y will fire. If the input is strong, both X and Y will fire. So this is, all of this seems fairly normal to us right now. But in the 1870s, this was revolutionary. And so believe it or not, these are the earliest artificial neural network models. If you ever wondered how far back the history of neural networks goes, as we know it, it goes back to 1873. And he also came up with some theory on how these things learn to store specific patterns. So when 2 impressions concur or closely succeed one another, the nerve currents find some bridge or place of continuity, better or worse, according to the abundance of nerve matter available for the transition. Basically, he says that when one neuron excites another, then it forms a connection between the two. He predicted what we now learn as Hebbian learning. So he came up with all of these rules. It was brilliant. It was entirely correct. But then unfortunately, this is from Bertrand Russell, the fundamental cause of the trouble is that in the modern world, the stupid are cocksure and the intelligent are full of doubt. So this happened with Alex Bain. In 1873, he postulated that there must be maybe 1 million neurons in the head with 5 billion connections. So it could acquire 200,000 concepts or percepts.
then 10 years later, he thought about it and he said, percepts don't just come fully formed. You have partial percepts in your head. And if you want to store all of those, you're going to require a lot more than 1 million neurons and a few billion connections. And eventually, there was a lot of opposition to him. Everybody thought he was stupid. And in 1903, he caved and he said, he apologized. He said, yes, I made a mistake. This is not how the thing works, and recanted. And he was correct when he first hypothesized the model, and he was wrong when he recanted. As it turns out, we now know that the human brain has enough material to store all of this and more. We have about 80 billion neurons in our little head, and we have something like 100 trillion connections. Then there's enough brain matter in your head to store everything that you will encounter in life and have something left to spare. So the human brain is, in fact, a connectionist machine, meaning everything that we do is based on the connections between the neurons. Neurons connect to other neurons, and the processing capacity of the brain is stored in the manner in which these connections are formed. So your artificial neural network is a connectionist machine. It emulates the structure. It's a structure comprising many simple units, like your neuron, which are connected to each other deeply. And the magic that happens is all in the connections, not the basic units themselves. So this is your connectionist architecture. It emulates the human brain. Now, this differs from your standard phone, right? What is the architecture of the processor in your standard computer? Anybody know? I'm sure you do because it's on the slide, right? This is called a what's it called? You must have heard of the von Neumann architecture. What is the von Neumann architecture? Anybody? Anyone know? Someone must know, right? Can I pick a random name here? All right. So the von Neumann architecture says that has a processing unit and a memory that's separate. And the memory holds the data and the programs. So the operations that the computer performs depends on the programs. If you wanted to perform something different, you change the program. If you wanted to operate on a different data, you change the data and the memory. By separating the processing, central processing, and the memory and programs in this manner, you can use the same processor to do all kinds of things. For example, you have your laptops or your phones. The same laptop can perform millions of different operations, have millions of different applications, and that's because you just change the program in the memory. In the connectionist machine, the architecture of the machine itself is the program, because what the computer can do, what the machine can do, is based on how the basic units are connected to one another. If you wanted to perform a different operation, you've got to change the computer itself. Now, this is not a very great architecture because, requiring a new computer every time you want a new program can be kind of expensive, which is why most of the time we emulate connectionist machines on von Neumann architectures. But there's a fundamental difference between your neural network architectures, which are connectionist, and the standard processor architecture that you have on your computers and your phones. And so to recap, neural network-based AI has taken over most AI tasks. These originally began as computational models of the brain, or more generally as models of cognition. And the earliest model of cognition was associationism. And the more recent model of the brain is connectionist, where neurons connect to neurons, and the workings of the brain are entirely in the connections between the neurons. So current neural networks models are all connectionist machines. We have a poll, 2 questions here on Piazza, post number 21 and 22. I'll have my lapel mic in the next class, so it should be better.
Anybody want to answer the first question?
Yes. Thank you, right? What about the second? Anyone want to answer the second question? Yes. 100 trillion. How many connections exist? 100 trillion, right? It's enormously large. Thank you. If you have not responded yet, it's okay. Please shut your laptops. We will continue, right? So the answer is to the first question is Alex Bain. And to the second question, it's 100 trillion. So here we are. These are connectionist machines. These are networks of processing elements. And all world knowledge is stored in the connections between the elements. But what are these elements themselves? For this, we're going to go back to the human brain. The basic unit of the human brain is the neuron. And this is what the neuron looks like. It's got a head, which we call the soma, and lots of little connections through which other neurons connect to this neuron. Now, roughly speaking, if the total signal coming in from all the other neurons exceeds some threshold, the neuron fires, and that firing goes down this long leg and branches out to many outgoing connections to other neurons. This is the basic structure. And just some factoids, because neurons, it's the connections between the neurons that really matter. You cannot replace neurons, which is why once your brain is formed, it's not going to change. If you have some brain damage, you can't just regrow those neurons, because if you did, the connections would not be there. Whatever information was stored in them is gone, along with the connections. And so you're basically fully formed by the age of 2. And another interesting thing is that this long leg is protected by a whole lot of fat, those little orange things. It's called the myelin sheath. And it turns out that how intelligent you are depends on how much fat you have in your head. So being a fat head is a compliment, right? This was actually true of Einstein. They've studied Einstein's brain. They found that he has exactly the same number of neurons as everybody else, but he had a lot more fat in his head. Now, so that's the basic model, right? But we want to computationalize it. And the first computational model for it was by these two guys, McCulloch and Pitts. McCulloch was a professor in the University of Chicago at that time. And Pitts was a homeless guy who came and knocked on his door and ended up spending a few months with McCulloch, and they came up with the first computational model of neurons. And I'm sure you just took one side at it, look at this, and immediately figured that this was the homeless guy and this was the prop, right? So, anyway, so here was their model, the McCulloch and Pitts model. When Pitts first came up with this model, he did all the math. And I still can't understand the paper that they wrote. It's pretty complicated here. And he was only 20, and he had never finished school and never been to college. So it was pretty amazing. He ended up as a prof at MIT. So this is what the model looks like. They said that every neuron has two kinds of connections. Excitatory synapses. So signals that come down the excitatory synapse make the neuron fire. And inhibitory synapses, if anything comes down the inhibitory synapse, the neuron will not fire. And they showed that just using this simple mechanism, you can construct pretty much any Boolean gate. And so another of their innovations was to show that you can think of the entire brain as a giant Boolean machine which performs Boolean logic. So here, for example, is one. If the first neuron fires, it connects to the second neuron through two connections. So one time instant later, whatever the time instant is, the second neuron will fire. So this is just a delay. Here, now the neuron fires only if it gets 2 inputs. So for this neuron to fire, both 1 and 2 must fire. If only one of them fires, then neuron number 3 gets only a single input and it will not fire. So what Boolean gate is this? Anybody? Right? And what would this be? If the neuron will fire if there are 2 inputs, what is it going to be? That's an OR, right? If either the first one or the second fire, it gets 2 inputs, and so it's going to fire. And this is a little more interesting. The first one must fire, and the second one must not fire. So it's 1 and not 2. So as you can see, these things can form pretty complex. They can perform Boolean logic. And then they can even emulate all kinds of phenomena that we observe in the real world. So for example, if you touch something very hot, or something very cold. Your instant response, if you touch it very briefly, you'll actually feel heat. It's only when you continue to hold it for a little while that you actually sense the cold. And they showed how this model can actually emulate this behavior. Here, for example, if you have a cold receptor and a heat receptor, and a heat sensation and a cold sensation, if you touch the cold receptor very briefly, then 1 second later this, or one instant later, this gets the sensation from here. But 1 instant later, it gets only one input. One is not enough for the cold sensation to fire. So it will not fire. But if you keep holding, keep sensing the cold, 2 instants later, you're going to get one going down this line and the second going down this line, and you will actually sense the cold. So you have to sense the cold long enough for you to actually feel it. On the other hand, if you just had a very brief cold input, you're going to get one that goes through this a little bit, then that goes out here, and then that goes out here, and you actually feel heat. But if you continue to hold the cold, sense the cold, at the second time instant, this one is actually going to be inhibited by the inhibitory connection over here, and so you won't feel the heat. They came up with this very interesting architecture which shows that just their basic model can model many of these interesting phenomena that we see in the real world. So this was the landmark that actually started off all of the work on artificial neural networks, but it was kind of incomplete. They showed that their networks can model small classes of functions, that if you have a tape, it's actually Turing complete. But they didn't prove any results, and they didn't come up with a mechanism whereby this network could learn to perform certain behaviors. So for example, if you wanted the brain to learn associations, they came up with no computational mechanism by which the associations could actually be learned. For that, we waited for this guy, Donald Hebb. So he wrote a book called The Organization of Behavior in 1949. Like all the people of those days, he was another interesting character who tried being everything from a farmer to a hobo to a teacher before he went off and did his PhD. So this book is where he wrote this very complicated paragraph, but then it's summarized these days as neurons that fire together, wire together. The basic idea was this. Again, the question is, we are trying to figure out how neurons learn to connect to one another and how they learn the strength of their connections. And he observed that in a synaptic connection, the two neurons don't actually touch one another. The first neuron has this bulb called the synaptic knob, and anytime the neuron actually has some excitation, it's going to release some chemicals. And those chemicals flow from the neuron to the second neuron, shown by the red bar. Now, if the excitation of the first neuron causes the second neuron to also get excited, then the bulb becomes slightly larger, which means the next time around, a firing of the first neuron is more likely to cause the second neuron to fire because the surface is larger and there will be more chemicals released. Now, you can put math to it, and you can see that the weight of the connection between the two neurons, X and Y, has the behavior that anytime both X and Y are 1, this weight will increase. So WXY equals WXY plus eta times X times Y, where X and Y are binary. Now, this gives you an idea, this gives us a mechanism for learning how the weights between neurons are formed and how they get strengthened. But can anybody tell me what's wrong with this? Anyone? Yes?
How do they get weaker?
They never get weaker, right? These always get stronger. So if you wait long enough, eventually every connection is going to be really strong. It's going to be a useless network. So this was fundamentally unstable. Stronger connections continue to enforce themselves. There's no notion of competition. There's no reduction of the weights. And so learning is unbounded. Now, this Hebbian learning is a pretty good idea. We still use it in many machine learning algorithms. And it has this function. And we need an update on this one as well. So for that, we had to wait for yet another insight. But first, here's another problem. people on Zoom hear me?
Yes.
Thank you.
Yes.
Okay, anybody want to answer this question? Someone on Zoom, do you want to answer this question? Anyone on Zoom?
Yeah,
Choices.
yes, so it's fundamentally unstable since there are no reduction in weight.
Exactly, right. So that's the problem with Hebbian learning. Thank you, right? Let's continue. So a better model was introduced by this guy, Frank Rosenblatt. Frank Rosenblatt was, again, a psychologist and a logician in Yale back in the 50s. And he came up with this model called the Perceptron. This was Rosenblatt's Perceptron. It's a very complicated looking model. He was trying to explain human vision. So he said that the human retina causes a whole bunch of neurons in the first layer, which he called the projection area, the A layer, to fire. And patterns on these of firing over here cause additional responses downstream. And he explained, he came up with a pretty good explanation for how the eye could potentially function. But then the key piece over here is this, again, there were a couple of innovations. The connections, the way he formulated it, the one neuron could have either an excitatory or a inhibitory influence on downstream units. This entire thing was what he called the perceptron. Now, within the perceptron, there's, if I want to draw a simplified version of it, this is what it looks like. Here would be your retinal sensory units. The first layer is what he called associative units. And the associative units responded to signals on the retina. And then the second layer was what he called the response units, which responded to patterns of firing in the associative units. Now let's focus on any one of these guys. What did these things look like? This is where his genius comes in. Each one of these units has this structure. It's a unit that gets inputs from many other units, which could either be sensors or other neurons. And corresponding to each one of these connections is a weight. So if the total weighted input exceeds a threshold, the neuron fires, otherwise it doesn't fire. It's a very simple thing. And he showed that just by having a structure based off just these units, you can get some very interesting responses. How interesting was it? He showed that this was at some point a universal Boolean machine. Using networks of this kind, using structures of this kind, like this guy here, or more explicitly this one here, you could compute any logical operation. And so this took up the public imagination so much that in 1958 you had the New York Times saying the embryo of an electronic computer that the Navy expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. This was in 1958. Frankenstein monster designed by the Navy that thinks, 1958, Oklahoma Times. So there was a lot of hype. And the hype was so great that expectations went through the ceiling. Of course, what came out didn't match the expectations. We ended up with the AI winter because the expectations were too high. And we found these things had limitations, and then they just stopped funding research in the area. Now, one of the problems that arose was that although Rosenblatt's model itself was this complicated structure with many units, the actual term perceptron began to refer to each of the individual units themselves rather than the entire structure. And the individual units look like this, as I said. Each of them has many inputs. If the weighted sum of all inputs exceeds a threshold, it fires, otherwise it does not fire. Even for these individual units, Rosenblatt actually came up with a nice learning algorithm. He showed how how this model could learn its weights to perform any particular operation based on the expected response. Now, the difference between Hebbian learning and Rosenblatt's model was that in Hebbian learning, if two neurons fired together, the weights got strengthened. There was no notion of a desired response. It was just random. Rosenblatt introduced the notion of a desired response, and the way he did it, he said a weight changes only if the output of a neuron differs from the desired response, and it's going to differ in proportion to how much it's off from the desired response. He showed that this learning rule actually converges for separable classes. We'll come to it in a couple of lectures. And he also showed how this model can now model all kinds of, just the basic unit can model all kinds of Boolean functions. For example, here, these are simplified illustrations of the Rosenblatt perceptron. The threshold is shown inside the circle. The weight of any connection is shown over the arrow. And so here, for example, the threshold is 2. If both x and y are 1, the total input is 2. It matches the threshold. Then this unit will fire. If either x or y are 0, then the total input is only going to be 1. It will not match the threshold, and it won't fire. So what's this gate here? Anybody?
And
That's an AND, right? Same thing. What would this one be? That's an OR. And here's an interesting one to the top right. What is that? That's a NOT, right? If x is 0, then the input is 0, so it matches the threshold. If x is 1, the input is -1. Note that the weight is -1. And so it won't fire. So it flips the input. It's able to perform all kinds of Boolean operations. Now, as we'll see in the next class, this model can actually perform something far more interesting and much more complex than just simple Boolean operations. But here's something it can't do. It can't compute an XOR. And the reason it can't compute an XOR, we will see it in a bit, but there's no setting of the threshold and weights whereby the output of this unit is going to be X XORed with Y. For that, we have to go back to see how to make this unit compute something as simple as XOR. We have to go back to the brain. And we find in the brain that you're not working with individual elements. You actually have networks of elements. And in fact, Minsky and Papert in their book, Perceptrons, an introduction to computational geometry, actually showed how these individual units are not particularly strong. But if you connect them up, you can perform more complex operations like this one, the XOR. So I can have one perceptron over here. This unit now is being called the perceptron. This guy computes X or Y. This one computes not X or not Y, right? And then you AND the two, and you're going to get an XOR. So just by connecting up these units, you can actually perform more complex operations. Now, here's a little bit of a terminology we will introduce at this point. We are interested in the output of this final neuron and not those of these guys. We don't really care what patterns happen over here. This is what is of interest to us. That's the XOR operation. So these intermediate units whose patterns are not particularly of interest, these are what we will call hidden neurons. And the unit whose output we are actually observing is what we will call the output neuron. Now, yeah.
Professor, I didn't understand how you got -1 for the hidden there.
Which one? So these are the weights. So this is, consider this. If X and Y are both 0, what is the output?
0.
So the threshold is -1. It's going to fire. Right? If X and Y are both 1, what happens?
1.
If X and Y are both 1, the total input is -2, which is lesser than the threshold. It will not fire. Right? So it's the not X or not Y. Right? So once you realize that you can begin connecting these things up to compute more complex Boolean functions, then you realize that you can connect them up to compute arbitrarily complex Boolean functions like this one. Right? So here's this is a multi-layer perceptrons where perceptrons are connected up in many layers. And this one is computing that really ugly function written on the top. And you give me a function. I can compose a network of perceptrons which actually computes the function. And so here's the story so far. Neural networks, which began as computation models of the brain, are connectionist machines. They comprise networks of individual neural units. The McCulloch and Pitts model represents neurons as Boolean threshold units, which models the brain is performing propositional logic. But they didn't give us a learning rule. Hebb actually came to us with a learning rule, but it was unstable. Rosenblatt's perceptron is a variant of the McCulloch and Pitts neuron with a provably convergent learning rule. But the individual units are limited in their capacity, but once you begin connecting them up, it can perform compute arbitrarily complex Boolean functions. But then our brain is not Boolean, right? We are not performing Boolean logic. The world is not Boolean. The stuff, just think of all of your perceptions. They're continuous valued. They're real valued. So how does this translate to real valued inputs and operations on real valued inputs? Again, it's very simple. We can make non-Boolean inferences and predictions with these units. So let's go back to this unit again. The threshold unit, the perceptron. But now assume that all of these x's are real valued. They're continuous. They can take a value between minus infinity and plus infinity. The same logic still holds. You compute a weighted sum of all of the inputs. If this weighted sum exceeds a threshold, the neuron fires. Otherwise, it doesn't fire. So how does this behave? To see that, I'm going to change the manner in which I represent this. I'll say that there are two stages to this operation. In the first stage, I compute a weighted sum of the inputs and add to it a threshold term. So this is an affine function of the inputs. And at the second stage, I actually apply a threshold function to this affine term, where the threshold function outputs a 1 if the input is positive, if this term, this affine term is positive, and a 0 otherwise. So these two are the same unit, just drawn slightly differently, right? So how does this behave? First, does anybody know the difference between a linear function and an affine function? Anybody? Yes.
You has to go to the origin.
That's it, right? So if I need to draw a picture, x1, x2, linear function will go through origin. An affine function is going to have still a line, but it doesn't need to go through origin. It has a intersection which is not an origin. That's it, right? So anyway, moving on, let's look at how this thing behaves, right? Let's do this here. This unit is going to fire if the weighted sum is greater than a threshold. So there's a boundary, right? When the weighted sum is exactly equal to the threshold, that is the equation of a line that doesn't necessarily go through the origin. And any input on this side of the line is going to, or this side of the hyperplane more generally, is going to result in an output of 1. Any input on the other side is going to result in an output of 0. That's it. And now once you realize how this works, this is what the actual function looks like. It's a Heaviside function. There is a hyperplane where the weighted sum is exactly equal to the threshold. On one side of the hyperplane, the output is 0. As the input goes to the other side, you get a step where the output now becomes a 1. And you can see why this can now compute any Boolean gate, right? So in Boolean functions, the inputs are all either 0 or 1. So if I had 2 inputs, these are the only 4 input patterns possible: 0, 0, 0, 1, 1, 0, and 1, 1. And if my perceptron drew its boundary between where the output is 1 and where the output is 0, right here, what gate is this?
Odd.
That's an OR, right? If any of the inputs is 1, it's an OR. This one here, and all I had to do is to shift the boundary. And now you can see why it can't do an XOR. An XOR needs 2 lines, right? We'll see that in the next class. And you can also see how this becomes an AND. But then things get interesting. How so? Let's say I want this decision boundary. I want the output to be a 1 inside the pentagon and 0 outside. How could I do this for using just this simple perceptron? I can start off with one perceptron which captures the lower boundary. The output is 1 above it and 0 below it. a second perceptron which captures this boundary. The output is 1 in the yellow region and 0 outside. A third one for this boundary, the fourth for this, and the fifth for this. And so now, observe that it's only within the pentagon that all 5 of them are outputting a 1. So I can just sum up their individual outputs, compare it to a threshold of 5, and the only time the output is going to be a 1 is when all 5 are firing, which is inside the pentagon. And so just by simply connecting these things up, I'm able to generate a pentagonal decision boundary, right? But then I can make more complex boundaries, like this one. If I want an output which is a 1 inside this double pentagon region and 0 outside, then I can have one subnet which captures this lower pentagon, a second subnet which captures the upper pentagon, then I can OR the two with a final output perceptron, and now I have a double pentagon decision boundary. But once I know how to do this, I can get more complex decision boundaries like these guys. All I need to do is to decompose it into a small enough number, into a number of convex regions. They don't even have to be convex, right? And connect them up. And I can have one subnet for each of these regions and OR the lot. And I can get some pretty complex decision boundaries. And so you can see that this a multi-layer perceptron is able to capture arbitrarily complex decision boundaries just by composing them just right. So think of a classification problem. Let's say I'm looking at images, and I want to figure out if this image is the digit 2 or not. Now, this image lives in some high dimensional space. For example, if you were working on the MNIST corpus, the MNIST corpus consists of 784 pixel images. So the input lives in some 784 dimensional space. In this 784 dimensional space, there's some region within which all the inputs that represent the digit 2 lie. And outside it, they're not the digit 2. And so if I want to build a 2 classifier, all I need to do is to compose a network that captures this peanut-shaped decision boundary in my figure. And we know exactly how to do it, right? Just using this little technique, which means that, in classification problems where we want to find decision boundaries in high-dimensional spaces, we can use MLP's multi-layer perceptrons, which are perceptrons connected in many layers, to compose arbitrarily complex decision boundaries. So MLPs are what are called universal classifiers. They are universal Boolean machines, Boolean functions, which means that given a Boolean function, I can always construct an MLP to compute it. They're also universal classifiers. You give me a classification problem, give me a classification boundary, and I will show you how to construct an MLP for that boundary. Pretty impressive, right? And so the story so far is that MLPs are connectionist computational models. Individual perceptrons are computational equivalents of neurons. The MLP is a layered composition of many such perceptrons. And they can model any Boolean function. They are universal Boolean functions. The individual perceptrons act as Boolean gates, and the networks of these perceptrons are Boolean functions. So for any given Boolean function, I can always construct an MLP for it. They're also able to model any decision boundary. Again, now the individual perceptrons capture linear boundaries, and complex boundaries can be composed by connecting up these linear boundaries. So MLPs can represent arbitrary decision boundaries. They are universal classifiers because they can classify data. So here's a point. Okay, this was an easy one. Anyone want to answer this question? How many perceptrons do I need? 7. Why 7?
Need the extra to get the eye.
So 6 for each of the boundaries, and the 7 to combine them all, right?
So again, you see how you get an idea of how you can begin composing any odd function, any odd decision boundary, any odd Boolean gate. But what about continuous valued outputs? So we know that we can use MLPs to construct Boolean functions. We know that we can use MLPs to compose, to classify, which means we can demarcate regions of the space and say produce 1 inside this region and 0 outside. But if you want to compute continuous functions like the one over here, where, for example, you want an MLP to compute a sinusoid, like sine of x, how would you do it? It turns out you can do that too. So here's a very simple example of a scalar function of a scalar input, just sine of x, for example, right? So for this, first let's start with this very simple unit. This one has an input x, and the x goes into 2 perceptrons shown by these 2 circles. This perceptron fires if the input exceeds the threshold T1, and this one fires if it exceeds T2. And without loss of generality, let's assume that T2 is greater than T1. Now, their outputs are combined once again, but with weights 1 and -1 respectively. So what happens? When the input is below T1, neither of the perceptrons is going to fire. So the output is 0. If the input is greater than T1 but less than T2, the first perceptron will fire, but the second one will not. So at the output, you're going to get a 1. When it exceeds T2, both of them will fire. They will cancel each other at the output, and the output goes back to 0. So which means that this little structure over here computes this function where the output is a 1 between T1 and T2 and 0 elsewhere, right? But once I know how to compute this, I know how to approximate pretty much any function. For example, if I have this ugly blue function over here, I can just break it down into many little cells of this kind, and then I can approximate the function within each cell using a pair of these neurons as we just saw, and we can scale the output accordingly and sum them up. And so now I can approximate the blue curve as this step function shown by the hull of all of the red boxes. And the error between the two can be made arbitrarily small by just making the boxes narrower. So I can approximate any function to arbitrary precision. So an MLP with many units can model an arbitrary function over an input to arbitrary precision. And this generalizes to functions of any number of inputs. So finally, before I get to this, there's a last point.
And the one thing that I skipped is that in the MLP, the way we said it was this was how we modeled it. This was how we modeled the perceptron.
It computed an affine function of the inputs, which was a weighted sum of the inputs plus a bias term. And then that affine term was put through a threshold function. This is what we call
an activation. And I could replace this with any odd function. The activation doesn't have to just be a threshold function. It can be pretty much
anything. So given that, suppose I have, answer this question. And let's see how this is. Anybody want to answer this? You don't need to get the answer. Just one?
None of the above.
Pardon me?
The answer is none of the above.
None of the above? Anybody else? Infinite. So if I'm allowed to change the activation function, over here the activation function is sine of x. You only need 1, but you only need 1, right? So the answer is none of the above. But I don't think I've made this quite clear, but so far, anyway. I'll take this off on Piazza. I'm just coming to the end of the class. The story so far is that multilayer perceptrons are connectionist computational models. They are classification engines. They can identify classes in the data. Individual perceptrons detect individual boundaries. And the network will fire if the combination of the outputs of the individual perceptrons falls within the decision boundary for the desired class of input. And they can also model continuous valued functions. These are all the things that we saw. So we've looked at it from a very high level. But then we've looked at a very specific kind of network where inputs go from, the information flows from an input to one set of neurons to the other, eventually to the output. You can make the models more complex. You can make them loopy, where the output of a neuron goes back to some other neuron earlier in the network. These are such networks, which were introduced by Lawrence Kuby in 1930, can actually model memory in the human brain, and we use them quite a lot. They can represent probability distributions over integer or real or complex valued inputs. They can model posterior and prior distributions. They can generate data from complicated distributions. They can do all of these things. And all of these operations are built upon the basic ideas that we just saw, that an appropriately configured and set up neural network can model pretty much any function, right? And I like to be facetious, so I used to joke that they can rub their stomachs and pat their heads at the same time. They actually have competitions for this, and it's usually won by an Indian. But this is lately they actually have robots which can do this, which is kind of surprising. Right? So the network is a function. The neural network is a function. Given an input, it computes a function layer-wise and predicts an output. So, or more generally, given one or more inputs, it computes one or more outputs. So when we go to this problem that we began the class with, what's in these boxes? These boxes each of these boxes is just a function. They take an input and produce an output. They take a voice signal, produce a transcription, an image, and its caption, a game state and another game state. So all of these can be modeled by neural networks. And that is, in fact, what we actually do. So in the rest of this class, in this course, we're going to see how this magic happens, how these functions operate, how we learn to take specific inputs and compute specific outputs to do all of the various kinds of operations that we just saw. And so for our purpose, for the introductory lecture, interesting AI tasks can be viewed or are in fact functions that can be modeled to arbitrary precision using a neural network. And in fact, that's what we're going to do. So to close out, we went through a brief history of networks, of connectionism, and its relation to cognition and the brain, and its contrast to conventional computer architecture. We saw some early models and their limitations. We introduced modern neural networks and what they can compute. In the next class on Wednesday, we're going to delve a little deeper into how neural networks compute their functions, what the notion of depth is, and what the limitations of neural networks are. So that's it. Thank you. If you have any questions, I'll take questions.